Okay, perfect. So good evening, everyone. I'm Claudia D'Amato from the University of Bari, Italy, and I'm going to present the work titled Embedding Models for Knowledge Graph Induced by Clusters of Relation and Background Knowledge. This is a joint work with Nicola, Flavio, Quatraro, and Nicola Fanizzi. Our starting point is given by...
So sorry, Ms. Amato. Your share screen button is not active. We saw your slides and then it disappeared. Could you please try once again? We cannot see your slides.
Okay, because I asked if the slides were visible.
Yes, they were. Now,
okay.
Yes, great, thank you.
Okay. Our starting point are knowledge graphs that generally come as the result of a complex building process, but because of that, they generally suffer of incompleteness and noise, and this is quite well known despite their live usage. And for this reason, knowledge graph refinement tasks are largely investigated, and among the others, particularly link prediction, which aims at predicting missing links between entities, and it is generally regarded as a learning to rank problem. And the triple classification, which aims at assessing the correctness of a statement with respect to a knowledge graph, and it is generally regarded as a binary classification problem. Because of the large dimension of knowledge graph embedding methods are largely adopted in the last few years, and they convert data graph into an optimal low dimensional space in a way to preserve graph structural information as much as possible. However, most of the methods that have been developed are grounded on closed word assumption or local closed word assumption, despite of the fact that knowledge graphs are grounded on open word assumption, and they almost disregard the schema level information and the reasoning capabilities that are actually available within knowledge graph. In order to cope with these issues, we developed an enhanced knowledge graph embedding methods, which is able to inject the background knowledge when learning embeddings, and particularly this is done by developing two components in the overall architecture of the knowledge graph embedding methods. One component is exploiting during the generation of the negative example, specifically by exploiting a deductive reasoner, and the other component inject the background knowledge when minimizing the loss function, particularly exploiting schema level information. Moving from this starting point, we decided to further enhance the model by exploiting a more fine-grained representation of the semantics of the relationship as proposed by Zan and colleague, which coded this more fine-grained representation as a tree structure, where the middle layer is given by the actual relationship. At the bottom layer, we find the clusters of relations that share kind of common meaning, and at the top level, we find sub-relationship that represent different nuances of the very same relationship. So in the end, we proposed Transar-Owl HRS, which is a knowledge graph embedding methods, which learns the embedding vectors by minimizing margin-based loss functions, which is composed by two different elements. The one which stands for LB is the loss function computed by the base model, which is Transar-Owl in our case, that is the one injecting the background knowledge when computing the embedding. And the other component standing for this LHRS is the loss function that is computed by considering the hierarchical structure that is computed exactly as a linear combination of each group of the embeddings in the hierarchical structures of the relationship having different weight. Indeed, now, rather than having just one embedding vectors for the relationship, we have three different components, one for the clusters of the relationship, one for the actual relationship, and the other one for the sub-relationship. As for the loss function of the base model, we actually modified the loss function of the base model that injected back on the schema level information by generating further triple, and specifically by exploiting the inverse of equivalent property, equivalent class, and subclass of axioms, by taking into account the clusters the relations belong to as computed by this summation here for each element. As for the score function, the original score function has been modified by replacing the embedding vectors for the relation with the linear combination, which is this component here of the terms which comes from the hierarchical structures. And it is important to point out that since trans-R is ultimately based on trans-R, the projection matrix need to be considered when projecting the entities to the vector space of the relationship. We experimentally evaluated our methods with respect to the baseline models that are trans-R-OWL, trans-R-OWL-R, and trans-R by performing link prediction and triple classification tasks. Specifically, we implemented, as suggested by Zan and colleague, the top-middle variant. That means we took into account only the top and the middle level of the hierarchy in order to keep under control the complexity of the overall model. As for for obtaining clusters of relationship, the K-mean algorithms has been adopted. Whilst for minimizing the loss function, the stochastic optimization via stochastic gradient descent and the optimizer momentum and AdaGrad have been implemented. We used knowledge graphs publicly available that are DBpedia 15K, DBpedia 100K, and DBpedia Iago, and we on purpose selected NEL, which represent a sort of stress test for our model, since NEL actually lack of equivalent class, equivalent property, have a limited number of type of triples, but it has an abundance of subclass of triples. So here the idea was to see if this abundance of subclass of triples could somehow compensate the absence of the other actions. And in order to have a better insight of the results, we distinguished both for link prediction and triple classification between all but type of properties and the type of only properties. As for link prediction, considering all but type of properties, actually our model, specifically by adopting AdaGrad optimizers, registered overall the best performances, with a slight exception for trans-R, where it performs slightly better on NEL dataset, which stands for our stress test. As for type prediction, again, our model outperformed the baseline model only on DBpedia Iago, NEL, and DBpedia 15Ks, while for the case of DBpedia 100Ks, which represented a larger and more complete data set, trans-R and trans-R was performing more successfully. For the case of the triple classification, all the models perform in a comparative way, while for triple classification, considering type of only relationship, again, our model, particularly using AdaGrad and momentum optimizers, outperforms the baseline models. So to conclude, we have proposed the trans-R HRS, which is a generalizable knowledge graph embedding methods for learning embeddings whilst exploiting the background knowledge and a more fine-grained representation of the semantics of the relationship. We implemented it as a system publicly available, and we proved improvement on knowledge graph refinement tasks, particularly when a limited number of knowledge is available. Whilst when considering more comprehensive data sets, we found out that exploiting the hierarchical structure does not play a big value added. For the future, we would like to extend the implementation of our system by considering the overall hierarchical structure, and we would like to formalize solutions for providing explanation for the predictive results. Thank you for your attention. I would like to remind you that Nicola Fanizzi will be at the poster session for poster 41, and I'll be happy to answer your question right now. Thank you.